Okay, today is Chapter 5, Section 4, Exponential and Logarithmic Equations. So now we're going to be taking what we've learned the previous, I guess it'd be 3 lectures, and learning how to solve equations. Right? Not the easy equations where we if we have to have the same base, or we have to have the same base either case, but not solving the easy ones where we need to have the same base. Now we're going to be looking at problems that do not have the same base, and then that's when it gets a little bit tricky. But again, in my mind, in my what's the word? I don't know. I'm kind of lost on words today. Anyways, in my mind, I think I've said this every section of this chapter, but I think this is fun, and we'll do it. But anyways, so far in this section, or let's see, we'll start right here. I've had too much coffee, can you tell? We've already solved exponential equations using the method of relating bases. So we can solve equations when we have the same base. That's easy stuff. However, when we don't have the same base, for instance, well, no, that's the same base as well. Let's do a for instance over here. And let's snip this. Okay, so for instance, let's say that we are looking at this, but suppose we're given an exponential equation in which the bases cannot be related, such as 2 raised to the x plus 1 power is equal to 3. There is no way we can get 2 and 3 to be the same base. Okay, so if we wanted to solve that, we have to do something a little bit tricky to both sides here. Okay, and again, this is what we snipped for the next page. Here we go, to find the x-intercepts. All right, so this is just trying to solve it using our x-intercept method that we've done before. Okay, but we can't solve it like that because we can't get the same base. All right, and look, turn your attention here. We can now use some properties of logarithms to solve this equation. Recall the following logarithmic properties. Okay, so if u is equal to v, okay, so the arguments, right? If u is equal to v, then we know that log base b of u is equal to log base b of v. Okay, we also know the power rule for logarithms, right? And the power rule is the most important part of this section because, again, if you recall the power rule, you take the exponent and you put it out in front, and that's where that r right there comes from. Okay, using that knowledge, we are able to solve these problems. We're able to solve this problem rather. Okay, so let's get to some examples. And the first example will be that first problem. Okay, so again, we can't necessarily relate these bases to one another because 2 and 3 do not have a common base. All right, so what we're going to have to do instead, okay, what we're going to do is we're going to take the natural log of both sides. Okay, so similar to how, so let's go ahead and write this real quick. Let's put a little gap there. Okay, so similar to how we could, if we wanted to, multiply both sides by 7. Okay, if we want to multiply both sides by 7, we can. We can do that because what we do to one side, we do to the other. Okay, so we're going to do something a little tricky here, but it involves obviously logarithms because we're knee deep in logarithms, but also the power rule. Okay, so what we're going to do is we're going to take the natural log of both sides. Okay, so we're just going to put ln here and ln there. Okay, we're going to take the natural log of both sides. And then by taking the natural log of both sides and using that power rule that we're familiar with, we can now take this exponent right here and put it out in front of the natural log, right? So this becomes x plus 1, which, by the way, always, and when I say always, I mean always, put your exponent out front in parentheses. And you'll see why here in a minute. Anyways, x plus 1, natural log of 2, and that's going to be equal to the natural log of 3. Okay. Now, real quickly, the natural log of 2 and the natural log of 3, those are actual numbers. And what are they? Natural log of 2 is 0.69, and the natural log of 3 is 1.09, or 1.1 if we round, okay? So those are actual numbers. They're just represented as a natural log, okay? But anyways, the reason why we put these things in parentheses every single time is because if we didn't put these in parentheses, then this particular problem, you might mess up and you might make it look like this. X plus 1 natural log of 2. Well, x plus 1 natural log of 2 is not the same thing as x plus 1 times the natural log of 2. Okay, so what we're going to do is we're going to get rid of these parentheses. So we're going to distribute this natural log of 2 through both of those terms. So we're going to have x natural log of 2 plus 1 times natural log of 2, which is just going to be, natural log of 2. We're going to keep that there for right now. And that's going to be equal to the natural log of 3. Okay, and then what we're going to do from here is we're going to isolate the x. Okay, we're going to isolate the x exactly like you might think we would. Okay, so let's go ahead and put this on the next page. So first thing I'm going to do is I'm going to subtract 1 natural log of 2 from both sides. And again, I said natural log of 2 is a number. I think we said it was 0.69. So it's essentially saying 1 times 0.69, right? So which is just 0.69. So I can pretty much just kind of, disregard the 1, right? 1 times anything is anything. And I'm actually going to do that to just kind of show. Okay. But anyways, we're going to subtract natural log of 2 from both sides. So we're going to have x natural log of 2 is equal to the natural log of 3 minus the natural log of 2. Okay, and then as mentioned, we're trying to isolate the x. So by isolating the x, over here we have natural log of 2, which we said 0.69, and it's being multiplied by some x. Okay, so naturally, what that would mean is, if this was 0.69, and we're trying to isolate the x, what would we do? We would subtract we would divide 0.69 from both sides. So that's what we're going to do here. Okay, we're going to essentially just divide both sides by natural log of 2. So we're going to end up with x is equal to natural log of 3 minus natural log of 2 all over the natural log of 2. And again, similar to well, any sort of fraction that we've seen before, these do not cancel out like that, okay? It doesn't work like that. So this would be our solution, okay? And that would approximately be 0.5850. Okay, and that's it. So our x, right? Ooh, that's not what I wanted. Our x value here is approximately 0.5850. Okay, and that's how we solved it. So that is how we. And honestly, as far as I know, it doesn't get any harder than that. Really, it's just remembering your algebraic rules. So let's move on and let's just test that theory that it doesn't get any harder than that. Tell you what, let's give this its own page so we can have some space for me to work. Alrighty. So A, we've got 3 raised to the x minus 1 power. Alright, now it appears that we can go ahead and change we can go ahead and use the like base for A, okay? Because I can see immediately that 1 over 27 is the same thing as saying 3 to the negative 3 power, right? We've seen and done problems like this before, so let's go ahead and do that where we relate the bases to one another. Okay, so A, we've got 3 to the x minus 1. That's going to be equal to, and then 1 over 27, as mentioned, we can rewrite that as 3 to the negative 3 power, and then my exponent there is 2x plus 1. Okay. And then we're going to, we know the power rule here. We can, we multiply, whenever we have an exponent raised to an exponent, we multiply. So this turns into 3 to the x minus 1 is equal to 3 raised to the, looks like negative 6x minus 3. Okay. And then here we have like bases. And then all we have to do is equate the exponents to one another. So we will have x minus 1 is equal to a negative 6x minus 3. And we do the algebra here. We put 4, 7, no, 2. We end up with x is equal to a negative 2/7. Okay. There we go. All right. And again, A is just basically what we've done before, where we got a like base. But B, we can tell immediately B is going to be a little bit different. But again, it's going to be in the same vein of as what we did in example 1. Okay, like I said, I don't think it gets much harder than example 1, and we're going to be putting it to the test for the remainder of these examples. Here we go. So B, all right, first thing I'm going to do is I can tell immediately. I mean, obviously, I have a base of 7, I have a base of 4. There's no way I can get these to have the same base. I can't do the like bases. So I'm going to have to take the natural log of both sides, in which honestly, and in many ways, in my opinion, I think it's easier. Okay, so we're going to go ahead and take the natural log of both sides, and I'll go ahead and put it in blue since I did that with the first example. So natural log of 7x plus 3 is going to be equal to the natural log of 4 and then 2 minus x. Okay, and then again, so did I change colors at all? No, I just went straight white. Okay, so we're going to now use our power rule here. We're going to put this in front of the natural log. Same thing over here. But again, we're going to put it in parentheses. Okay, the parentheses is very, very important because otherwise it would just look like, well, I'll show you again. Okay, so this looks like the left side here, it looks like it's just x plus 3 natural log of 7, right? But that is incorrect. It is not x plus 3 natural log of 7. It is x plus 3 times natural log of 7. And the same thing can be said over to the right. Okay, so that's why it's important to make sure you put that parentheses there. And of course, now we distribute. So we're going to say x natural log of 7 plus 3 natural log of 7. It's going to be equal to 2 natural log of 4 minus x natural log of 4. Okay, and let's see, this x, there we go. Split that up a little bit. All right, and then of course we're trying to isolate the x, so let's go ahead and what we're going to do here, well, it was, all right, so I'm going to go ahead and move this to the left side, right, by adding x natural log of 4 to the left, and I'm going to move this to the right side by subtracting 3 natural log of 7. Okay, so I'm not gonna do the whole minus 3 natural log of 7 both sides because I'm running out of room here. But that is what I will be doing, and so my problem will look like x natural log of 7 plus x natural log of 4. That's going to be equal to 2 natural log of 4 minus 3 natural log of 7. Again, all I did was I wanted to have my x on one side, and then of course my constants, again, as I said, these are actual numbers, right? They're decimal numbers, but they are actual numbers. Put them on the right side. So let's go ahead and snip this and put this on the next page. All right. So I'm trying to isolate the x, and so by isolating the x, we see that we have an x in both these terms, so I can factor an x out. Okay, so by factoring an x out, I will have x, and then I've got natural log of 7 plus the natural log of 4 That's equal to 2 natural log of 4 minus 3 natural log of 7. This gets pretty thick pretty fast, huh? And lastly, we're going to divide both sides by this so I can isolate the x totally. So I'll have x is equal to 2 natural log of 4 minus 3 natural log of 7 all over natural log of 7 plus the natural log of 4. Okay. Now at this point, and I'm pretty sure that the textbook, let's see what textbook, okay. Okay, so I'm going to do something just a tad different from the textbook. Okay, so the textbook, as you can see, right here. Well, no, it'd be right here. Oh, is that not? Oh, it is. It's writing in white. Okay. Put it in red. Okay, so the textbook, right here. Right. Notice from that step that's in a square. Well, not that one actually. Shoot. Good job, Sherman. There's got to be bigger. Can I not make that eraser bigger? I guess it just goes strictly from this one, huh? There we go. That's a thick eraser. Okay. So anyways, going from this down to this, okay? Notice what they did was we have the natural log of 16 minus the natural log of 343, because that's, well, that is, oh gosh. They did the power rule, and they put the 2 on this 4 and the 3 on this 7. Okay, well 4 squared is 16 and 7 cubed is 343. Okay, nothing new. That's something that we're very familiar with. Also, this subtraction sign, we know what the subtraction sign, it turns it into a division, right? It would become the natural log of 16 divided by 343. Okay, and then all this was put into the calculator, and the solution was negative 0.9199. Now here's the whole point behind all these red lines here. Okay, the whole point is right here. You can just put it into your calculator right now. Okay, now it's up to you. It's your prerogative. But as far as passing this class goes, as far as even getting to the next step, I mean, you're familiar with how to manipulate logarithms. You're familiar with the product rule and the quotient rule and all that stuff. I don't think it is necessarily, well, I don't think it's necessary to do these two steps to get to the final solution. Okay, so all you have to do is put it into your calculator. 2 natural log of 4 minus 3 natural log of 7 divided by natural log of 7 plus natural log of 4. Now obviously this is contingent upon you putting it into your calculator correctly, but if you do it correctly, then you can essentially, like I said, skip those 2 steps. Okay, and that's about it for that. Okay. Okay, so here we go. Here's some problems, again, just kind of incorporating things that we are familiar with, but now we're solving for an x. Okay, but again, the processes that we've done so far are incorporated here. So in A, we see we have a base of 25 and we see we have a base of 17. There's obviously nothing we can do here except for take the natural logs of both sides. So let's go ahead and do that. Natural log of 25 e to the x minus 5 power. That's going to be equal to the natural log of 17. Okay, and then of course doing our power rule here. On second thought, probably should have done something else first. Okay, so let's actually do one thing first here. and that would be to divide both sides by 25 actually. So let's go ahead and divide both sides by 25. The reason why is because, I mean, we could have continued on the same path that we just were on. It's just that doing this calculation now makes it just makes things a lot easier later on. So I'll go ahead and divide both sides by 25. So my equation now becomes e to the x minus 5 power. That's going to be equal to 17 over 25. Okay, so again, all I did was just divide both sides with 25 right off the bat. And now that makes it super easy to calculate. Okay, so again, we're going to take the natural log of both sides. So let's go ahead and put that on this line up here. Ooh. Okay, and then of course we're going to do our power rule. We're going to take this and put it out in front. So we're going to have x minus 5 natural log of e. That's going to be equal to the natural log of 17 over 25. Okay, and as we have seen, the natural log of e is just 1. Okay, so that was something that we did the other day, or Monday actually. We just put in natural log of e into our calculator and we got 1. So again, this essentially just kind of goes away, right? No big deal, because it is 1, and 1 times anything is anything. So this becomes x minus 5 is equal to the natural log of 17 over 25, and then one last step, we're going to add 5 to both sides. So we're going to have x is equal to the natural log of 17 over 25, and then we're going to add 5. And that is going to be approximately 4.6143. Okay, and that's A. All right, B looks ridiculous, but it's not, because we know all these rules, and hopefully, I mean, I know it's been a rough, long semester, and honestly, they all are, to be completely honest with you, somebody who's went through, many semesters, but hopefully you haven't forgot some rules here. In this particular case, we're talking about some exponent rules. Okay, so let's take care of that first. And we know that whenever we have like bases, and we're multiplying like bases here. Okay, the base here is e. Let's see here. The base is e. So what we have to do is we have to add the exponents together. Okay, so this is going to turn into, again, this is b. This is going to turn into e, which is the like base. That's going to be 2x minus 1. And it's going to be plus x plus 4. Okay, and that's going to be equal to 11. All right. Oh. And then continuing over here, we can combine like terms. So we're going to end up with e to the, looks like the 2 and 2x and the x combined, so it turns to a 3x. 3x. And then the negative 1 and 4 combined to get a plus 3. That's going to be equal to 11. Okay. We're going to take the natural log of both sides. So if we take the natural log of the left side, then that's just going to be equal to 3x plus 3, because again, we're taking a natural log here. This comes out front, and the natural log of e, well, that just becomes 1. Okay, so it just becomes 3x plus 3. And then the right side becomes the natural log of 11. And then we're just going to solve for x. So it looks like we're going to subtract 3 from both sides and also divide 3. So we're going to end up with x is equal to the natural log of 11 minus 3 all over 3. And that's going to be approximately natural log of 11 minus 3 divided by 3. So it'll be approximately 0.2007. Okay. All right, so these properties of logarithms, it's nothing new for you. It's just reiterating it because we're going to be using them here in a moment. But these are properties that we are familiar with. We've already went over them. Ooh, this is a good one. All right, so we've got, we just have to solve this particular problem. It says solve 2 log base 5 of x minus 1 is equal to log base 5 of 64. Okay, so looks like we have the same base, so that's good. All we have to do is equate the arguments with one another. Okay, well, before we equate the arguments with one another, we have to deal with this 2. And all we have to do is put that 2 log base 5 of x minus 1. Put that 2 right up there. And that's it. It's equal to log base 5 of 64. Okay, so all I have to do is equate the arguments with one another. So we're going to have x minus 1 quantity squared is going to be equal to 64. Looks like we're going to have a quadratic equation here. All right, so x minus 1 quantity squared, that is x squared, and that's going to be minus 2 times, let's see, is it? We can actually do it the other way. This way is a lot easier. Let's go and just take the square root of both sides. Okay, so if we take the square root of both sides, well, then the left side becomes x minus 1. And then what's this? We take, again, plus or minus the square root of 64. Well, the square root of 64 is 8, so I can just say plus or minus 8. And then if we add 1 to both sides, we end up with x is equal to 1 plus or minus 8. Okay, so there are 2 possible solutions here. X is equal to 1 plus 8, which is 9, or x is equal to 1 minus 8, which is negative 7. Okay, so what we're going to have to do is we're going to have to look at the argument there. Okay, because again, what can the argument not be? It cannot be 0 or what? How about this? It has to be greater than 0. Okay, it cannot be less than or equal to 0. So we have to, kind of plug this in. These are pretty easy. We can just do this in our head, right? If we plug in a 9, well, 9 minus 1 is 8, so 9's good. So let's go ahead and 9's good. All right, but negative 7, if I plug in a negative 7 there, well, negative 7 minus 1 is negative 8, so negative 7 is not good. Okay, so my only solution here is 9. And as I mentioned in the previous lecture, you have got to check these each and every time. Okay, there's no situation where you should not check these. Okay, so this problem you might get caught up in autopilot mode. Okay, so I say that because when I'm in the classroom, there's a lot more communication between instructor and student. I usually put up an example, I give students a minute or two to solve it or at least think about it, and then I go over it. Okay, obviously in online format it's not the same. I can't expect that from students. But with that said, whenever I would put this up on the board, many of my students would just be like, "Oh, I don't know, I'm done. I'm done skis." Right? I forgot how to do this. How do I do this? All right. Well, remember this. We convert. What we're going to do is we're going to convert this from a logarithm to an exponential. Okay, what I mean by that is we can change this from log base 4 of 2x minus 1 is equal to 2. We could change that to exponential as 4 squared is equal to 2x minus 1. right? That's the exponential form, right? So, and of course we know 4 squared is 16, so we can say 16 is equal to 2x minus 1. We can go ahead and add 1 to both sides and then divide by 2. So this tells me my x is going to be equal to 17 over 2. Okay, and then what we're going to have to do is we're going to have to plug that in to make sure that it works. Okay, well, if we plug in 17 over 2, well, 17 over 2 means 34 over 2, which is 17. 17 minus 1 is 16. So 17 over 2 works. And that's it. All right, and I'm pretty sure the next example is very similar. We just have to think back to the very beginning of this particular section. Okay, so kind of the same thing. Now this. Let's see, I'm pretty sure we're towards the end of this section already. One more. I think that might be like, yeah, one more example for this one. This is the culmination of everything we've learned in this chapter so far. Okay, so let's begin. We have a same basis here. We are also adding these two logarithms to one another. So if we add the two logarithms to one another, we know that we must multiply the arguments. So we multiply the arguments, log2, and then by multiplying the arguments, it becomes x plus 10 times x plus 6, and that's equal to 5. Okay, so that is what this problem looks like when we condense it down. All right, now we're trying to solve for x here, so now we can change this to our exponential form, right? So now we can change this to 2 raised to the 5th power is going to be equal to x plus 10 times x plus 6. Right? And then we can continue the computation here. 2 to the 5th power is 32. And then we will FOIL this right side out, right? FOIL, 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 FOIL. So we'll have, it looks like x squared, and then 16 and 10, I'm sorry, 6 and 10 gives me 16, so plus 16x, and then plus 60. And then we can subtract 32 from both sides, so we're going to end up with, and I'm going to put the 0 out. Let's go put the 0 on the right. Again, it's a thing I prefer, and I'm sure many of you prefer it as well. So we're going to subtract 32 from both sides to get 28. So we're going to have x squared plus 16x plus 28. That's going to be equal to 0. And 7 and 4. Okay, so this does factor nice and neatly. So the left side factors into x plus 14 and x plus 2, that's equal to 0. And that means that we have x is equal to negative 14 and x is equal to negative 2. Okay. Now, at the end of the section on Monday, I said just because you have a negative solution does not mean that it is not a solution. You have to plug it in. Okay. Now again, I know this because I was a student. I was a student that when things went in one ear, it immediately went out the other ear. I don't know if it went in one ear, to be honest with you. I think it just like stopped right at the ear canal. But anyways, my point is this. Here's an example of just because it's negative doesn't mean that it doesn't work. Okay. Well, if we look here at our arguments. Okay. So in the first one, it appears that my x needs to be greater than or equal to 10. Well, not greater than or equal to 10. It must be greater than 10. Okay. And this one, it must be greater than, I'm sorry, negative 10. And this one must be greater than negative 6, right? If I plug in a negative 14, okay, well, negative 14 will not work, right? Because negative 14 plus 10 is what? That's negative 4. So that's immediately not going to work. Okay, so this tells me that that does not work. Okay, but negative 2. Well, if I plug in a negative 2, well, negative 2 plus 10, well, that's good. That's positive 8, sorry. Negative 2 and positive 6, well, that's going to be a positive 4. So this tells me that the negative 2 does indeed work. Okay. Now, the thought process here was I looked at both the arguments. Okay. Realistically, I really just have to look at the most restrictive argument. Okay. And what I mean by the most restrictive argument basically means that, okay, so I'm looking at the first one. Put another arrow there. Nah, I guess I can highlight with this. Look at the first one. Okay, and I know that my x value must be greater than or equal to. Does that say that right? Yeah, this must be greater than 10. I keep saying or equal to. I'm sorry. It must be greater than 10, and this one must be greater than. Oh gosh, must be greater than negative 10. It must be greater than negative 6. Well, the negative 6 is the more restrictive argument, so that's the one I would look at the most. Does that? I don't know if that makes sense. Let's see if I can rephrase that. All right, here's a better rephrase. Just put it in both. There we go. It's easy. It's not like it's hard. I feel like more brain cells are being expelled here trying to explain which one to look at, and when realistically, in any of these problems, you could just do it in your head in like a second or two. So we'll just do it that way. Whew. Oh, we skipped. I can't wait for many years from now when I go back and rewatch these videos. I'm probably going to cringe so hard, aren't I? And I'm pretty sure, okay, good, I didn't skip anything. Okay. All right, last problem of the semester. Let's make it count. We've got the natural log of x minus 4 minus the natural log of x minus 5. So that minus immediately tells us, this minus right here, tells us that we're going to use division. Okay, so let's go ahead and rewrite this with our division. So we're going to have the natural log of x minus 4 divided by x minus 5. That's going to be equal to 2. Okay, so we know that the natural log, okay, so let's see, this is essentially written like this. Log base e x minus 4 over x minus 5 is equal to 2. Okay, that's essentially what the natural log is, right? It's just a log with a base of e. And with that said, hopefully it becomes abundantly clear that if I want to change this into, if I want to turn this into exponential, then this is the same thing as saying e squared is equal to x minus 4 over x minus 5. Okay. That's the best way I can explain it, and I think that's pretty good. Right. So anyways, moving on. We still need to solve for x. This looks like a doozy, so looks like we're going to have to multiply both sides by x minus 5, so let's go ahead and do that. So we multiply both sides by x minus 5, we'll end up with e squared times x minus 5 is equal to x minus 4. Again, we're trying to get the x's on one side, and by separating the x's, obviously that's counterintuitive, isn't it? Well, the thing is, we have to get rid of the fraction, so we multiply both sides by x minus 5. And then next, let's go ahead and distribute that e squared through. So we're going to end up with e squared x minus e squared 5. Honestly, I probably could write it the other way, 5e squared. But we're just going to roll with this. It's equal to x minus 4. And now it should be obvious what I'm trying to do here by trying to get these x's together. So I'm going to go ahead and I'm going to add, well, I'm going to add e squared times 5 to the right side. I'm going to subtract x from the right side and put it to the left side. So we're going to end up with e squared x, and then it was minus x, and that's going to be is equal to e squared times 5 minus 4. Minus 4, let's fix that up. Alrighty. And on the right side, we're going to factor. So let's go ahead and put this on another page so we're not running out of room and writing small. We're going to factor an x out of the left side here. So we factor an x, and we end up with, it looks like simply an e squared minus 1. That's going to be equal to e squared times 5 minus 4. Man, that looks so bad. I really should have just wrote 5e squared. Oh well. And then of course we're going to divide both sides by e squared minus 1, so we're going to end up with x is equal to and if I were to put this in my calculator, I'm going to get something pretty crazy here. So it's not too crazy. Not any crazier than anything I've done today. So 5.1565. Okay. And that's it. I don't know. That's it. And that also concludes all the lectures for this semester.